All right, so this is just some more examples of our integral test, and we've already shown this in the previous video, so let's get started. Our three conditions are that our function f, in this case our f of x is going to be our a sub n, which is 1 over x squared plus 2x plus 2. So we need to show that it is continuous, positive, and decreasing from 1 to infinity. And so let's go with positive first. There are no subtractions here, so this is definitely positive. So we're going to be plugging in from 1 to infinity. And if there are no subtractions, there's no way for our denominator to be 0, so it is continuous. So now we just need to show that it is decreasing, and that is our derivative. So if we take the derivative, and I rewrite this as x squared plus 2x plus 2 negative 1, you can already see it when I take the derivative, I get negative. Oops. To the negative 2, which would be negative 1 over x squared plus 2x plus 2 squared, which is obviously negative. So this means that it is decreasing. Just noticed that I spelled continuous wrong. There's an extra U in there, not O, continuous. And so that checks as well. So now we can move on to show. So if our integral converges, we know that this series is convergent. If our integral diverges, we know it is divergent. And so we go back to what we did in 7.8, and that's the limit as t approaches infinity. And we're starting at 1 to infinity of 1 over x squared. Sorry, that wouldn't be infinity anymore. That's t of x squared plus 2x plus 2. Now, obviously, we can't use u substitution on this. So we're going to make this into a nice little perfect square. So we do x squared, oops, not there, x, and then again we take half of that 2, so that's 1. And then whatever we have there, we do have to add to it. So that means there would be that extra 1 in here, sitting here like that, is 1 squared. And so we have to subtract 1 to cancel it, so minus 1 plus 2. And so we end up with the limit as t approaches infinity of 1 to t, 1 over x plus 1 squared plus 1 dx, and there's our arctan. So inverse tangent of x plus 1 is what we would get from t to 1. And now if we plug in t, we would get the limit as t approaches infinity of inverse tangent t plus 1. Oop, don't have enough room. Let's move it over. Minus inverse tangent of 1 plus 1, we'll just say it's 2. Now, we know with inverse tangent, it's going to go off to, as t goes off to infinity, so your inputs of your inverse tangent go off to infinity. That means we're going to be going to pi over 2 because it's reversed. So this would become pi over 2 minus inverse tangent of 2, which means convergent. So that means our series from n equals 1 to infinity of 1 over n squared plus 2n plus 2 is convergent by the integral test. Let's put that as one giant box. That looks better. And there we go. And so there will be, in later videos, we're going to be learning some other tests, and you'll be able to look and notice that this is going to be convergent based on what it looks like. So you're just going to be confirming it with the integral test. Let's try another one. So if we look at this here, we can tell that it is positive because, again, we're going to go from, in this case, 2 to infinity. So again, we're not going to have any negative values being put out from this. And then it's decreasing. And we're going to have to show that with a derivative. And then continuous. Well, we know there's no denominators here that are going to give us a 0 because we don't have our ln of 1. It's outputted of it. And that's not going to happen there. So again, continuous. Now decreasing. So our f of x here is 1 over x ln of x. And then now we're just going to rewrite this. This is x ln of x to the negative 1. And we got to take our derivative. So f prime of x equals negative, and that's what we want to see, x ln of x to the negative 2, and then now a little product rule. So that would be derivative is ln of x plus, and then it would be 1 and 1 over x, which gives us 1. So we end up with negative, I'm just going to leave it that way, ln of x plus 1 over x ln of x. Again, it's decreasing, so check. So now we can go off to our integral. And so we're going to get the limit as t approaches infinity, integral in this case 2 to t, of 1 over x ln of x dx. And now that's a u sub, so I'm going to do it separate, 1 over x ln of x, that way I don't have to mess with the t's and moving it around. So u equals ln of x, du equals 1 over x dx, and so that's a nice clean substitution. There's our u, there's our du, so we end up with the integral of 1 over u du, which is the natural log of u. Okay, so I'm going to shrink that down, move it over there, and we continue with our limit. So the limit as t approaches infinity of the natural log, and our u here is ln of x, so this will become ln, I can get rid of that parenthesis now, right, of ln of x, like this. Okay, so we would have that ln of x, and then we're going to go from t and 2. So this would equal, let me move that down a little bit and over, and we're going to put a little squiggly line here around that stuff for just our conditions. All right, so this is the limit as t approaches infinity of the natural log of t, and we're going to go off to infinity, so I'm going to throw away those parentheses, minus the natural log of 2. And so you can sit here and play with it some more and really modify it into more limits, like a limit of an s or whatever you want. But obviously ln of t, as we plug in infinity, that's going off to infinity. And then if that's going off to infinity, that natural log is going off to infinity. So this is equal to infinity, which means it's divergent. So, why am I putting a box around it? We're not done, huh? So that means our sum from n equals 2 to infinity of 1 over n ln of n is divergent by the integral test. So it's because it hit the continuous positive decreasing. If the integral is divergent, then so is this. Because again, this is going to be an overestimate of our integral. So as you can see here, there's our series, right? And then the integral itself. And so this integral here, which is 1 over x ln of x, is diverging. So if that's diverging, then of course anything bigger than it's diverging. And then for the other one, the first one, you can see that our integral is converging. So anything below it is also going to converge.